Welcome back again. Today we're going to talk about the electromagnetic spectrum or light. So, the electromagnetic radiation propagates through space as a wave moving at the speed of light. So, the speed of light is equal to 3 times 10 to the 8th meters per second. C is equal to nu lambda, or frequency times wavelength. So the speed of light is equal to the frequency times the wavelength. So since the speed of light is a constant, we can calculate frequency or wavelength using this equation. So frequency is in units of hertz or inverse seconds, and wavelength or lambda is in units of meters. If it's not in units of meters, you have to convert to the units of meters to be able to use this equation. So the energy of electromagnetic radiation is directly proportional to the frequency. So the higher the frequency, the higher the energy of that radiation. So E is equal to h nu, which h is Planck's constant, nu is again the frequency, and E is equal to energy in joules. So energy in units of joules, h is Planck's constant, which again, it's a constant, so 6.626 times 10 to the negative 34th joules seconds, and nu is frequency in units of hertz, which is in inverse seconds. So long wavelengths have low frequency, which also have low energy, but short wavelengths, high frequency, have high energy. So this is the electromagnetic spectrum, a way to kind of visualize it. Radio waves are about the size of buildings, and then you go to humans, or in the radio microwave transition, microwaves about the size of butterflies, infrared about the size of a needle point, visible spectrum is about the size of protozoa, ultraviolet light is about the size of molecules, X-rays about the size of atoms, and gamma rays have wavelengths about the size of atomic nuclei. Now this is all the wavelengths that we're talking about. Frequency goes from very low frequency in radio waves all the way up to gamma rays, which have a very, very high frequency, and the temperature of objects at which this radiation is the most intense. So as you heat things up, you get the black body radiation effects, which allow them to emit things that you can see. So there is a point where you can see visible light temperature ranges. So if you heat things up, they start to glow. This is because of this black body radiation effect. So let's use some of those equations. The first one, calculate the wavelength of a photon if the frequency is 5,000 hertz. The first question to ask yourself is, what equation do you need? So the equation you need is C is equal to lambda nu, or C is equal to wavelength times frequency, the value of C. And the value of C is 3 times 10 to the 8th meters per second. What is your unknown? Your unknown is the wavelength. They want to know what the wavelength is, or lambda. And then solve the equation for wavelength. Wavelength is equal to C over frequency, the speed of light divided by the frequency. So plug and chug, plug those numbers in. What's your answer? Next problem, calculate the frequency of a photon if the wavelength is 500 times 10 to the negative 9th meters, or 500 nanometers. What equation do you need? So we're calculating a frequency from a wavelength, so we need C is equal to lambda nu, or the speed of light is equal to the wavelength times the frequency. The value of C, again, it's a constant, 3 times 10 to the 8th meters per second. What's your unknown? Unknown is our frequency. Solve the equation for frequency. Frequency, or nu, is equal to C over lambda, speed of light divided by the wavelength. Plug those numbers in. Speed of light, 3 times 10 to the 8th meters per second, divided by 500 times 10 to the negative 9th meters, and we get our answer. Calculate the frequency of a photon if the wavelength is 600 nanometers. Again, we need to convert that nanometers to meters, so we're going to multiply it times 10 to the negative 9th to get it to meters. What equation do we need? We're going from a wavelength to a frequency, so same equation, C equals lambda nu. Convert to meters first, so 600 nanometers is equal to 600 times 10 to the negative 9th meters. Now calculate the frequency. Same thing, rearrange the equation, plug those numbers in. What is the energy of a 500 hertz photon? What equation do you need? You need energy is equal to h nu, Planck's constant, times nu. What's the value of h? 6.626 times 10 to the negative 34th joule seconds. What is your unknown? Unknown is energy. Solve the equation for energy. It's already there. E is equal to h nu. So plug those numbers in, Planck's constant times the frequency, get your answer. What is the frequency of a 5,000 joule photon? So we still need the same equation, E is equal to h nu, but we're given the energy instead of the frequency. You calculate the frequency by rearranging the equation, so frequency is equal to E divided by Planck's constant. Plug in those numbers and get your answer. Calculate the wavelength of the same photon. So you have your answer in frequency, you plug that into the other equation, C is equal to lambda nu, and solve for wavelength. So wavelength lambda is equal to C divided by frequency, and that'll give you that answer.